Good morning, everybody. It's a Saturday morning, and I was thinking about one of the muddiest points that we talked about on Thursday. So I typed up this selected proof. I know that some of you all may have seen this posted on Twitter already. I had 2 JPEGs that I sent up, but I wanted to go ahead and maybe give a little explanation in case there were still some questions. So the proof that we were talking about was let the set S be the set of vectors V1 to Vp, and let them be a set spanning some subspace W. We want to show that if there exists a vector v sub k in this set S, which is a linear combination of the vectors in S, the set S is linearly dependent. So what we're trying to show here is that if we have this set of vectors v1 to vp, if there's one vector in there that's a linear combination of any of the others, then that's enough to show that the set S is linearly dependent. So what we're going to need to make sure we know in order to complete this proof, we need to understand and know the definition of linear independence and dependence, and then we just need to manipulate some linear combinations. So let's look at the proof. So first of all, without the loss of generality, we're going to consider a smaller set, and we're going to call that B, and just assume that that set B has only 3 vectors in it, B1, B2, and B3. And this set has the property that B3 is a linear combination of B1 and B2, such that C1 over C3B1 plus C2 over C3B2 is equal to minus B3. So what we assumed here is that we could have made a linear combination of those 3 vectors, C1B1 plus C2B2 plus C3B3, that was equal to 0. Of course we could do that. And then I just rearranged those and solved for minus B3 because we were told that there was one vector, and I'm assuming that vector is B3, that was a linear combination of the other 2, namely B1 and B2. So if we rearrange those terms, then what we get is C1 over C3B1 plus C2 over C3B2 minus B3 is equal to the 0 vector. Now what does that mean? Well, that means since there's a linear combination of the 3 vectors equal to the 0 vector, for which all of the coefficients are not 0, this implies the vectors B1, B2, and B3 are linearly dependent. And that's because our definition of linear independence states that the only way the set of vectors is linearly independent is if the only way to combine them and get the 0 vector is for all of their coefficients or weights to be equal to 0. And so since we can see that that linear combination above is set up such that the vectors B1, B2, and B3 are combined to be the 0 vector, and in particular B3 has a coefficient of minus 1, this implies linear dependence of the set. So I hope that helps a little bit, and if you continue to tweet me your muddiest points, then I will continue to create these responses.